In this video, we'll discuss how to implement the code to determine a connected component for a graph starting for a given index of a vertex. Now, we'll consider an undirected graph that is numbered. So the vertices will be from 0 to maximum number of vertices minus 1 will be the maximum number of vertices. And the index that we receive, it's the index of one of the vertices in the graph. To compute the connected component, we'll use a Boolean array of markers. And this will keep if a given vertex with the corresponding index is or is not in the connected component. So if the marker is true, means the vertex is in the connected component. If the marker is false, means is not in the connected component. Also for optimization, we'll count how many elements we have in the connected component. So this count will be the size of the connected component that is determined. To initialize our search, we'll receive the graph and the index for which we want to compute the connected component. And initially, we'll just initialize local fields, local variables, graph and vertex index with received values. Then we'll check if the uh, vertex index is a valid index, needs to be between 0 and the maximum number of vertices minus 1. So if it's not a valid index, we'll just throw an error specifying that it's invalid vertex index. Next step is to initialize a Boolean array of markers, and we create this array with the same size as the number of vertices in the graph, because for each vertex we'll keep if it's or not in the connected component. And for we'll initialize the array with false, because initially we'll consider the no vertex is in the connected component. And also we'll put the size of the connected component to 0. Again, we have it's the initial step. We haven't added any element in the connected component, any vertex. Now, we'll call a recursive method using depth first search to add the first vertex, the vertex index, to our connected component. And we'll discuss how this depth first search method is working. So it will receive a vertex. Initially will be the vertex index, but then we'll receive other vertices. And for the assumption here is that this vertex index was not yet visited, was not yet added to the connected component. So it's a new vertex that we want to add to our connected component. So what we need to do, we'll increase the size, because now we add the vertex index, we add the new one in the connected component, so increase the size of the connected component. And also we mark this vertex as being in the connecting component, so we make the in the Boolean array of markers, we mark this position as belonging to the connecting component. We make it true. Then we'll take all the adjacent vertices. So I am now in a vertex. I am looking towards the neighbors, all the adjacent vertices, and for each of them, I will see if I need to go explore the direction or not. How? I am looking if it's this adjacent index it's marked or not. If it's marked, I do nothing, because this means I already passed through that node before. I already treated that node and added it to the connected component. So I don't need to worry anymore about the node, so I do nothing. If it's not marked, means that this adjacent index, this neighbor, it's a new element that needs to be added to my connected component. So I call recursively the method to add this adjacent index to the component. So after I do all this process again for the adjacent index, I will come back here and take a new adjacent index of my vertex, and I will explore all the adjacencies for my vertex. When I finish, I know that I explore from this position in all possible directions and edit all the connected element vertices to my connected component. Now, um, this will fulfill the computation of the connected component. To access the results, we have some methods. First, we check if the entire graph is connected, and to do so, we can look at the size of each connected component, and if it has the same size as the graph, means they are the same. So I compare the count, which is the size of the connected components, with the number of vertices in the graph. Now, we also can get the size of each connected component by returning the count. But also we may want to get the entire connected component, and we'll get it as an array of integers in which all these elements will be the elements of the connected component. To build the result, we'll start by creating an array that has a size, a length of the size of the connected component. So we create an array of integers with the count size. And then we'll add to this array all the nodes that are marked as belonging to the connected components. So we'll have an index, a vertex index, that will go from 0 to the number of vertices. So we'll look to all the vertices in the graph and we'll increment one by one. And uh, if this vertex belongs to the connected component, so its mark is belonging to the connecting component, then we'll add the vertex to the connected component to the result. How we do that? We start with an index for the connected component, then initially is 0, and then as we go, if we find that vertex that must belong to the connected component, we'll add it to the current position in the connected component, and we'll increment also the position of the index in the connected component. So now we'll be able to put on the next position the next element that we found. So at the end, this will add all the elements from the connected component to the result, and we are able to return the result, which is a connected component.